Good morning. So we are moving on with chapter 17. We've started thermodynamics, and we're going to start off with this conceptual question, opening a tight jar lid. We got a jar lid, it won't come off. There's a glass jar, there's a metal lid, and what this is saying is if it's too tight, run some hot water over it. The hot water will raise the temperature of the metal faster than it will the glass. And we've got an expansion coefficient on the metal expands, it's going to open that up, and that can help us get a tight jar lid taken off. So maybe something you're already familiar with. So there's the understanding of what that does for us. So volume expansion, now we've already talked about volume expansion, so we can move through this pretty quickly, I think. Volume expansion is similar to the linear thermal expansion. We were looking at both types last presentation. So the volume expansion is going to be relevant for liquids, and again, it's really not useful for gases. Gases, the expansion on gases is going to depend on what the pressures are. So if we know that there's a steady pressure, then we can actually come up with expansion coefficients. But it turns out that once we look at gases as ideal gas, once we start using the ideal gas equation, we'll deal with gases there. So I'm going to say, no, these are not going to show up in our table. This is the formula that we use. Now notice before we talked about beta as a three-dimensional expansion or a volume expansion, and we see that the formula looks pretty much the same, except now it's in terms of volumes. So, and then beta is just going to be equal to 3 times alpha, and you can run up and down the tables and see that. So what this is going to be useful for is both solids and liquids. And the example we're going to think about here is a gasoline tank. I don't know if the gasoline tank's in the sun, if it's underneath my car, but increasing and decreasing temperatures. So how do we, we're going to take a steel gasoline tank on my car, which is not out in the sun, 70 liters in volume, and we're going to start off at 20 Celsius. So the idea, at least initially, is that the gasoline is at 20 Celsius and the gasoline tank is at 20 Celsius both. And then what happens if the car warms up? So it does sit out in the sun, and as a result, the temperature of the tank goes up to 40 Celsius. So the tank is going to go up to 40 Celsius and the gasoline that's inside. All right, so here's that expansion problem. Now we are going to work in terms of volume, and we're going to do this as a three-dimensional problem. That says that the tank starts off at 70 liters, and we look up the alpha linear expansion, but we can multiply by 3. Now I just multiplied by 3 and got 36. I think the table said 35. But this is 36 parts per million of expansion. Now I've written this as per kelvins. And the reason for that is if I'm working with a formula that involves delta T is the same in Celsius or kelvins. Kelvins are defined in a way where they're the same size as Celsius units. And that says, well, let's try this out. If I start off at 20 Celsius and the temperature goes up to 40 Celsius, that's an increase of 20 Celsius. Now, if I start off at 20 Celsius, in kelvins, that would be 293. And if I end up at 40 Celsius, that would be 313. Well, if I work with the 293 and 313 numbers, that gives me an increase of 20 kelvins. So anytime we calculate a delta T, a difference between two temperatures, Kelvin and Celsius are interchangeable. Now that's not always going to be the case, but for delta T formulas, it is. And this is a delta T formula. So I've just written it in kelvins just to remind myself, so I'm just kind of conceptually teaching myself, hey, kelvins work the same way as Celsius for these expansion formulas. So I put in 20 kelvins and it cancels out the units on per Kelvin here. What I'm finding is that the volume of the gas tank actually goes up. It goes up from 70 liters to 70.05 liters. I'm getting an extra 0.05 of a liter in the gasoline tank itself. Now, when I look at the gasoline expansion, what I find is that the volume expansion here is 950 parts per million. That's a lot more than the 36 parts per million I'm getting for the steel. What it seems like is the gasoline is expanding at like 3 times as much as the steel expands. So the expansion that we're going to end up with here, same formulas. What we're looking at is the expansion coefficient times the reference volume, and then the temperature increase. What I'm finding is the gasoline expands by more than a liter, 1.33 liters of expansion, whereas the steel tank only expanded by 0.05. So taking the difference between those two numbers, it says that 1.28 liters is going to somehow spill. Now, I don't know if the tank is sealed, maybe there's a cap on there and it's tight, the pressure goes up, but if we leave this open, it's predicting that we'll have 1.3 liters of gasoline that expands out of this tank. Doesn't sound good. And so that's why the gas stations, when you are putting gasoline into the tank, at some point it shuts down, it automatically shuts down, won't let you put more gasoline in. They don't want you to overfill your tank. If you're filling up your tank early in the morning and the temperature's really low, and you fill it right to the top, then and then for some reason you don't drive very far and then you set it out and the temperature goes up, you're going to run into this problem. Okay, you're going to have excess gasoline inside there. Now, another thing to be aware of with purchasing gasoline, at a gasoline stand, is that gasoline is not sold by mass, it's sold by volume. And so that tells us that gasoline, when it's denser, is actually going to be less expensive. Getting a liter of gasoline in the morning at a cold temperature is actually more gasoline than a liter will be later in the day when that gasoline has expanded. So that's why you see all the physics and engineer sort of individuals getting their gasoline at 4 a.m., right? Go out when the temperature is the very lowest, get the most gasoline for the price. Anyway, maybe you could go out at 4 o'clock and see, and ask people who are getting their gasoline at 4 o'clock why they're doing that. It does give you a little bit extra gasoline purchasing it at a lower temperature. Okay, so that's a good problem, right? Looking at expansion rates between it. Now right here is a table showing what expansion is like in water as a function of temperature. So, water has some of these, I guess they're unusual properties. Water has, well, the thing we're running into here with water is that at familiar everyday kind of temperatures, we do observe water going liquid and then water freezing, right? So if it's cold in the winter, temperatures could easily drop to where water freezes, and then at higher temperatures the water liquefies again. And so what happens is we don't have a nice linear expansion rate. Now in the table, they told me that water has a certain thermal expansion rate, but that's not reliable once we get down to temperatures close to freezing. And everyday temperatures, even at 20 Celsius, water is getting down into the region where this is no longer a linear effect. So when we do calculations using these thermal expansion coefficients with water, even at room temperature, there's going to be error introduced into that. So that there's not one thermal expansion coefficient that's going to work well for water over the familiar range of temperatures. So water's kind of a special case. You really have to almost look that up for the range of temperatures that you're working with, and it's not going to be a linear effect. The formulas for it are going to be more complicated in general. All right, we talked about this a bit too, that when we have expansions that take place, let's say we have a building or a bridge, and we've built it, and we have not allowed for thermal expansion. What happens then when the temperature goes up? Well, if I've placed a bunch of blocks of some material right against each other, and thermal expansion takes place, that's going to create stress in that material. And so what we're looking at here is, we're actually going back to chapter 12, where in Physics 4a you guys looked at stress inside materials. If I exert a force on something, I can compress it to a smaller shape. So what we're going to do is we're going to take two sorts of effects here. We're going to take the thermal expansion effect that we just talked about, and what we're going to add to that is the elastic modulus, or the Young's modulus effect for materials. So these materials are also, they can be compressed by exerting forces on them. So you can think of this as kind of a two-step process. So what's going to happen here then is that, and here's the problem or the example we're going to be looking at. The example we're going to be looking at is, let's say we've got a bunch of concrete blocks set up. And we've got this concrete set up in a way where the concrete blocks have been placed right next to each other. If the temperature goes up, there's no way for these blocks to expand. That means that they'll end up being under stress. If the temperature goes high enough, due to thermal effects, we could fracture the concrete. Concrete could actually fail as the temperature goes up. So it says this. It says we're going to start off at a temperature of 10 Celsius. We have 10 meters of 10 meter long concrete blocks. The temperature is going to go all the way up to 40 Celsius, and then it says the cross-sectional area. It turns out we don't need all these numbers to solve for this, but what we can do is we can look at the 10 Celsius going up to 40 Celsius and then ask ourselves, how much stress is that going to produce? So here we go. Here are the concrete blocks. I drew what looks like a concrete block here, I hope. So we're saying that there's a length of 10 meters, a starting temperature of 10 Celsius. We're going to take that all the way up to 40. At 10 Celsius, the blocks are placed right next to each other with no room for thermal expansion. We're going to get a delta T then of 30 Celsius, which is the same as a delta T of 30 Kelvin. So I'm thinking of this in two steps. I'm thinking of this as step one is a thermal expansion would take place. If they were not packed next to each other, we would get a certain amount of thermal expansion. That's step one. Step two is, now that the thermal expansion has taken place, how much force would be required, or how much stress would be required to now take those blocks that have thermally expanded and squeeze them back to their original length. And that will tell us how much stress these blocks are going to be under when the temperature goes up to 40 Celsius. So I did this thermal expansion calculation. Delta L is alpha L naught delta T. I put all the numbers in. It turns out I ended up with the same expansion coefficient when I looked that up in the table. Now, just like there's thousands of types of steel, there's thousands of types of concrete, right? And so when I looked this up, there were a range of values given, but 12 was kind of an average or a common value for the expansion for concrete, 12 parts per million. So I used that. Now the blocks themselves are 10 meters in length, so I put that in. That gave me 3.6 millimeters of expansion. Now if you notice, both the thermal expansion and the compressive strength formulas have factors of L naught. And so it turns out that the answer we're going to get in this problem is actually independent of L naught. I'm multiplying by L naught in the first part, but I'm dividing by L naught in the second part. So it's really independent of that. So the L naughts actually factor out, but I went ahead and calculated it just so we could see what the numbers are. So for 10 meters of length, for every 10 meters of length, we're going to get 3.6 millimeters, or we would have gotten 3.6 millimeters of expansion. Now we didn't get that because the blocks were constrained. And that says that we can now go in and ask, well, how much stress would be enough to compress these by 3.6 millimeters? And here I'm using, again, the formulas from chapter 12. So we're looking at compressive stress rather, sorry. So compression stress. Following the formulas there, I had to look up the elastic modulus for concrete. So the elastic modulus for concrete I looked up as 20 times 10 to the 9th newtons per meter squared. And what that gave us, plugging into the formula, was a compressive stress of 7.2 10 to the 6 newtons per square meter. Okay, so this is how much stress the concrete will be under. Now, you'll notice in engineering now, you guys are all, many of you may already be taking material science, for example, or will be taking material science in the future. And I think it becomes more and more standard in engineering, rather than reporting this as newtons per square meter, to go ahead and write it in pascals, units of pressure. So it's some million pascals of stress. Since stress is measured in newtons per square meter, we can use pascals for that. And so 7.20 megapascals of stress that we've placed the concrete in. Now, these are just some numbers I looked up for the concrete. It said that the elastic modulus for concrete, 20 times 10 to the 9th newtons per square meter. That also, in engineering classes, I think in your engineering classes, material science, that's going to get listed as 20 gigapascals. 20 gigapascals is the elastic modulus for concrete. Now, I also looked up, I went back to chapter 12, looked this up. The ultimate strength for concrete is concrete can tolerate 20 times 10 to the 6th newtons per square meter, or 20 megapascals. At 20 megapascals, concrete will begin to fracture. So it turns out, for the numbers given, at least the calculations I ran, and again, you guys, check these numbers. If you see something that doesn't make sense, stop by office hours and let me know, or send me a message. Send me an email or something. Let me know if you feel like I've got some errors, because we want to catch those immediately and get that information out to the class. In any case, what we had calculated for the compressive stress introduced by this temperature increase is 7.20 megapascals, and what I'm seeing from looking at the table is it can actually survive 20 megapascals of stress. So far so good. The concrete, maybe it wasn't the best design that we came up with because we didn't allow for thermal expansion. But under these conditions, up to 40 Celsius, the concrete survives. It will begin to fracture at 20 megapascals, and the stress that we created at this higher temperature was only 7.2. Okay. All right. So that wraps up thermal expansion, linear thermal expansion, volume thermal expansion of solids and liquids. Now what we kept saying is, every time they tried to introduce gases into thermal expansion, we said, no, we don't really use those expansion tables. With gases, what we do instead is we come back and derive a different formula, a formula that includes the effect of pressure. Solids and liquids under pressure don't really change volume very much, but gases do. Gases are very sensitive to pressure changes. So we've got to come up with different formulas. For gases, we are going to come up with something that includes volume, pressure, and temperature. And then we need to have something that tells us what the sample size is for the gas that we're looking at. These are often represented on what we call a PV diagram. Now, PV diagrams can be used for gases, liquids, and solids, but we're going to start by using these PV diagrams a lot to start thinking about how gases and what the properties of gases would be. Something to be aware of is if we have a sample of some kind of a gas and it's staying at a constant temperature, that these constant temperature contours are hyperbolas on our PV diagram. They have this kind of shape to them. So we're going to start seeing that over and over again. So what happens is, let's say we take a collection of gas molecules, we put them in some kind of a container. If we now compress the container, right, what's going to happen inside is the pressure is going to go up. Now, whether or not the temperature goes up depends on whether that container is thermally isolated or whether it's able to exchange thermal energy with its environment. So gases, we have to keep track of temperature, pressure, and volume all at the same time. Now, on the other hand, it turns out that with gases, the formulas we come up with are probably more reliable. So we've got an extra variable to keep track of, but the formulas we get are going to easily represent all types of gases, all compounds, pretty well. So that's kind of a trade-off. Now with gases, again, we had talked about defining temperature, and we said that temperatures are defined in a way, we want to define a temperature scale so that temperature is directly proportional to the amount of kinetic energy in the molecules, and this works most easily when we look at samples of gas molecules. Gas molecules behave, well, we say it's ideal behavior, that most gases do behave in a way where as the kinetic energy goes up linearly, the temperature also can be defined to match that amount of energy. So that turns out to be very useful. And that's what these plots are showing, is that the volume, I guess this is the volume effect, the volume goes up proportionally with temperature. Now what we can do with gases also is we can do measurements of absolute zero. If we keep lowering the temperature on a collection of gas molecules, they're going to take up less and less space. The pressure is going to drop off. They're going to be taking up less and less space. Once that pressure has dropped to zero, or once that volume of the collection of molecules has dropped to zero, we are at absolute zero. So absolute zero is defined at, the temperature at which the pressure of a gas will just drop to zero. And that's what this is all saying. Again, the absolute temperature scale. So they're introducing that idea of pressure is proportional to how fast the gas molecules are moving. If the gas molecules are moving fast, then there's higher pressure within that sample of gas molecules. As they slow down and eventually stop, the pressure drops to zero. And that pressure dropping to zero effect, we want to define that as the temperature going to zero because there's no more kinetic energy in the molecules at that point. So now this I had to leave in. Some of these slides I've just taken out because I didn't feel like they were that useful. It says, why should you not throw a closed glass jar into a campfire? And that's just, that seems like not a very good idea for a number of reasons. If it's a glass jar and you throw it in, I'm guessing the glass is going to shatter. I think what they're looking for in this is if you set, I don't think they want to say throw, if you set a glass jar or you place a glass jar in a fire, the gas inside a closed glass jar, sorry. The gas inside is, the molecules are going to go faster and faster, the pressure goes up, it's going to shatter the glass. That glass jar could explode. But this is, I don't know, it just sounded like a funny thing to do. Oh, let's throw a glass container into a fire. All right, how are we going to represent these properties of pressure, volume, and temperature in gases? And what we just said was that the pressure and volume are proportional to temperature, and they're proportional to how many molecules are there. Now there's different ways of keeping track of how many molecules are there. We could just count the number of molecules. I think that's the most obvious way. We could divide the molecules into moles and then say how many moles we have. Now that's probably convenient for calculations. So I could count how many molecules, or I could count how many moles of molecules I have. Another way we could do this is we could measure how much mass. Now, the mass is going to be related to how many molecules are there. So any of those approaches should be a way that we can determine how much material, how many gas molecules we have in a container. So we're going to come up with what the book is calling molecular mass. I'm going to refer to this as molar mass, and we actually already talked about this back at the beginning of the chapter. We already went over some of these calculations. So for example, if I take a collection of H2 molecules, hydrogen, each molecule of hydrogen 2 has a mass of 2 atomic mass units. When I scale that up to an entire mole, 1 mole would have a mass of 2 grams. A mole of neon has a mass of 20. That comes from looking at the periodic table and seeing what the molar mass is for these different compounds. For carbon dioxide, what I want to do is take the molar mass for carbon and then the molar mass for oxygen, and I got to take 2 oxygens and add those all together. That's looking at the periodic table. That's on average 12 plus 16 plus 16 gives me 45. So again, just going back and introducing this idea of using a molar mass. Now, to show up where these to show how these numbers in the periodic table can be calculated. Now, one thing you can do is you can take naturally occurring whatever element you want to look at. I chose neon as an example. If we look at the periodic table, it says that neon has a molar mass of 20.18 grams. Now that's a little confusing because since protons and neutrons have a mass very, very close to 1 atomic mass unit, why am I getting something that doesn't match up with an integer? I would expect this to be much closer to 20, right? But it turns out neon has 10 protons, but there's an isotope that has 10 neutrons. There's an isotope with 11, an isotope with 12. These 3 different isotopes of neon are stable. Now there's a bunch of radioactive unstable isotopes also, but these are the 3 stable isotopes that make up naturally occurring neon. There's an abundance. So of each of these isotopes, turns out that 90%, or better than 90%, of the neons naturally occurring in nature are the neon 20 isotope. A little more than 9% are the neon 22, and less than 1%, are a neon 21. So if I take a sample of neon, it says that if I take 1 mole of each of these isotopes, each one individually is going to be very, very close. These are not exact. But neon 20 is almost exactly 20 grams per mole. Neon 21 is almost 21. Neon 22 is almost 22. And then if I multiply by these abundances, what I'm going to end up with is an average molar mass. So that's what the periodic table is giving us. It's giving us an average of the different isotopes that make up naturally occurring the naturally occurring abundances of those elements. Okay, so something to be aware of when we're looking at these molar masses. All right, here it is, the ideal gas law. We're going to be working with this a lot, a real lot. So this is something we want to be clear on. If we take almost any gas, what we find is that the sample size, which here is given in terms of moles, the pressure, the volume, and the temperature are going to follow a certain pattern. And they almost all gases are using the ideal gas formula. We're going to get calculations of the properties of almost any gas, accurate to within 1% or better, using this one formula. So it's really handy that all different types of gases all follow, many of the same. They have many of the same properties, and so now to make everything match up here, it turns out if you take pressure and volume and temperature and number, the units don't cancel out. So there is some kind of a constant that we have to introduce. Now it's referred to as the universal gas constant because this one constant works really well for almost all types of gases. So the gas constant is going to get written as big R. In standard units, that's 8.314 joules per mole per Kelvin. Now it's given in some different units here, but I am not really going to be using that very much. You of course want to be aware that when we change units, the constants, the numerical values of the constants will change as we change units. But we are pretty much going to stick with big R in standard units. I know in chemistry classes they often will introduce 3 different values of R depending on which sets of units they happen to be working in terms of. But again, we're going to stay with standard units all the way through. I think we're going to be just using that first value. Now, the ideal gas law can be written in the form we have here. It can also be written in terms of the number of molecules. So instead of combining the molecules into what we call moles, what you can do is just count how many molecules are there. Now, the disadvantage of working in terms of numbers of molecules is there's a lot of molecules in any sample of gas that we might look at. So what you end up doing is bringing in a lot of scientific notation because there are huge numbers of molecules. So in most situations, it's easier to work in moles, but again, I want to think in terms of just a kindergartner. For a kindergarten, the most basic way to look at these molecules is just count how many are there. 1, 2, 3, 4, count all the molecules. If you do that, you get a formula that looks very much the same, but we have to change the value of R because it's not in terms of moles anymore. In fact, instead of referring to it as R, we now use little k, and it's called Boltzmann's constant. Ooh, I didn't write that down. Write that down. So that's referred to as Boltzmann's constant. It's considered one of the very fundamental constants within physics, and Boltzmann's constant is a conversion factor that says at this temperature, this is how much energy the molecules have. So the value for Boltzmann's constant is 1.38 10 to the minus 23 joules per Kelvin. So how much energy per Kelvin will the molecules have? Now P, V, and T here are pressure, volume, and temperature. Pressure, if we're going to go in standard units, pressure needs to be in pascals or newtons per square meter. Volume needs to be in cubic meters, and temperatures have got to be kelvins. You've got to have an authentic, reliable temperature scale where 0 really means 0, and that means we're going to be working in kelvins. Okay, so that's what the ideal gas law looks like. Let's practice some problem solving with the ideal gas law. Now, for some reason, I don't know why we've done this. I want to claim this is more of a chemistry thing. there is what's called standard temperature and pressure. Now, it turns out that, as you might expect, standard pressure is defined as 1 atmosphere. That makes sense, because so many of the measurements that we do, if we go into the lab and we try and do some kind of measurements, typically we're working with something close to atmospheric pressure. So that makes sense. For some reason, we have defined standard temperature as 0 Celsius. Now, for lab purposes, the reason 0 Celsius is standard temperature is because you can recreate a chemical reaction, say at standard temperature, by putting it in an ice bath. An ice bath, which means water with some ice floating around in it, will always be at 0 Celsius if you give it a little bit of time to reach thermal equilibrium. But engineering tends to take a different approach. Almost always in engineering, tables of material properties are based on 20 Celsius, not 0 Celsius. So you gotta pay attention to homework problems. So in the textbook, when they talk about STP, the temperature they're talking about is 0 Celsius. But if we're working at a different temperature, that's going to change the values of what we calculate. So watch for that. Standard temperature is defined to be cold. Now what this says is figure out the volume of 1 mole. And so I did do that. What I did was I took standard pressure, 1 atmosphere, and converted that into pascals. So 101,300. Now, back in Physics 4a, and I wasn't teaching, in Physics 4a when we talked about this, we pointed out that pressure can also be, units for pressure, can also be written as joules per cubic meter. So I always like to keep that in mind because for many calculations, joules per cubic meter turns out to be really handy. So you can think of pressure as an energy density, and that's why joules per cubic meter works. So here's our collection of gas molecules. Again, to describe this collection of gas molecules, I need 4 quantities. I need volume, pressure, temperature, and number of moles, or number of molecules. All right, so they're telling us to take 1 mole, which is 6.022 10 to the 23rd molecules, and then standard pressure. Now standard temperature they're saying is 0, so that's going to be 273.15 kelvins. And what I'm doing is taking the ideal gas formula and solving for volume. That's what they wanted us to do. I plugged all the numbers in. The units begin to cancel out. The moles cancel out, the kelvins cancel out, and the joules cancel out. Remember, the pressure can be written as joules per cubic meter. And so the units that are left are volume units, and the volume that I got was 0.02242 cubic meters. So that is the predicted volume of 1 mole of an ideal gas, a gas that's behaving ideally, and we'll see what that means. And then it's at 0 Celsius, or 273.15 kelvins, and it's at 1 atmosphere pressure. That worked out to be 22.4 liters. But remember, that's only at 0 Celsius. So that's not something that you can use at other temperatures or other pressures. If we change the pressure, or if we change the temperature, that, or the number of moles, that volume is not going to be the same. Okay, so it's only at that one set of conditions that we got that value. Now, in this example, here we are moving on to another example. 1711, we got a helium balloon. It wants us to find out, I'm going to go ahead and move on to my notes here. So there's a helium balloon. It says it has a diameter of 36 centimeters, so I divided that by 2 to get the radius. And it says that it's at 20 Celsius, or maybe I put that in. It says that it's at a pressure of 1.05 atmospheres. So I got this balloon blown up, and the pressure inside's just a little bit higher than the pressure outside, and that keeps the balloon, stretched out. So the balloon's squeezing back in, and that extra pressure is pushing out, and it's balancing. So the pressure I ended up with, 106,365 joules per cubic meter. Temperature's got to get converted into kelvins, 293, and it's asking us to find out how many moles. Now I got the pressure, I got the temperature, I know what big R is, the gas constant, and I'm ready. I've got all the numbers, except what we have to do is figure out what the volume is. Now it says that the balloon is spherical. I don't know, when you blow up these helium balloons, they're not exactly spherical, but close enough, I guess. So I'm using the sphere formula, finding out how many cubic meters we've got of volume for that balloon. So plugging all the numbers in, I ended up with 1.067 moles. So, about 1 mole. So I'm thinking, here's a balloon, it's about this big, and it contains about 1 mole of gas molecules, regardless of what gas is in there, whether it's helium or hydrogen or oxygen, or if it's got these pressure and volume and temperature values, it's going to be about 1 mole. So that applies to whatever type of gas might be in. Now, they wanted us to say how much mass of helium is in there. And so what I want to do now is take that number of moles, 1.067 moles, and then use the molar mass of helium. So helium, the molar mass, 4.0026. Turns out that naturally occurring helium is like 99.9999% helium-4. And so the molar mass here is essentially 4. I've got 4.27 grams of helium. That's how much mass there is. So that's important. So with these ideal gas formulas, you definitely want to be able to switch back and forth between numbers of moles and mass. That's an important skill. All right, how about the mass of air in a room? So, and the room that they're asking us to look at in this example is 5 meters by 3 meters by 2.5 meters. So now they said STP, and I don't want to be in a room where the temperature is 0 Celsius. So I'm going to change that. So just so you guys know, I'm going to change the numbers here. I'd be freezing if the room in here were at 0 Celsius. So I'm going to raise the temperature up to 20 Celsius. So, I needed to write that in too. So write in 20 Celsius here, which is 293 kelvins. So I realize I'm not quite following the instructions they laid out on that previous slide. All right, the room I'm in right now, actually, it's roughly that size. I guess it's about 5 meters this way, it's about 3 meters this way, and it's about 2.5 meters. So I'm thinking, hey, this is kind of like the room that I'm in right now. And again, it's at 20 Celsius, so it's not freezing in here. It's comfortable. And so to find out the mass of the air in the room, I'll just do the same thing we did on the last example. I need to find the pressure, the volume, the temperature. I'm guessing the pressure in here is about 1 atmosphere. I went with 20 Celsius, which is 293 kelvins. And then I used their values for the volume, 37.5 cubic meters. I put in the gas constant, 8.314 joules per mole per Kelvin. And what I came up with was 1,559 moles of air. Okay, so that's how many moles of air molecules I have in the room. And like we were saying, it doesn't matter what the air consists of. It could be nitrogen or oxygen or whatever. And the number of moles doesn't really depend on what the composition of those gas molecules is. Now, it turns out that air is 78% nitrogen, 21% oxygen, 1% argon. And then air is also complicated by the fact that the amount of water in the air can be anywhere between basically 0 and super dry days. So you can have weather where the humidity drops to practically 0. But you can also have times when the air, several percent of the air molecules, you can go as high as, a few percent, I think, is water. And so that's a variable. And so what I did was just took it out. I took out the effect. I'm solving, assuming that the humidity in here is 0. So what I did was this. I took that 1550 moles of air. Now I took 78% of those and said that of those 1559 moles of air, 1216 of those moles are nitrogen. And 327 moles are oxygen, 16 moles are argon, just by using the fractions. And then I took the molar mass of each, multiplied those, and found out, in this, kind of modestly sized room here, there are 34 kilograms of nitrogen, 10.5 kilograms of oxygen, and 0.64 kilograms of argon. Now, let's stop and think about that a minute. That's not 0. When I walk through the room, it doesn't feel like there's very much resistance. I really don't notice air resistance very much. Maybe when the wind is blowing, very firmly, we start to feel that effect. But it almost feels like there's nothing in here, when in reality, there's 45 kilograms of air. That's over 100 pounds. There's more than 100 pounds of air in just this room. That's a lot of air, right? That's quite a bit of mass of air. If we condense that down, put it in a container, set it on a scale, it would come in at over 100 pounds. Come in at 45 kilograms of air. That's a lot. All right, another way of solving problems using the ideal gas formula is often the amount of the gas won't change. If I have something where the container is, the volume is changing or decreasing, maybe, but the actual number of molecules is not changing, I can use ratios to reduce the ideal gas formula to here. By the way, I cross this out with a red line because that's a misconception that gets used sometimes. That 1 mole of an ideal gas is 22.4. That is not true in general. That was only true at 0 Celsius, 1 atmosphere pressure. So again, it's kind of a misconception that gets passed along. All right, otherwise, everything on here looks good. Here's an example. It says that we're going to check the tire pressure, and the gauge pressure comes up at 200 kilopascals, and after driving, the temperature is going to change. So what pressure is within the tires? I think I am going to leave that up to you guys to take a look at. So I'm going to move on. I do have that in the notes here, but I am going to move past that. And one reason for that is I think I didn't get everything calculated correctly. So I'm gonna get that corrected, and then you guys can take a look at the setup and how that gets solved. Here we're going back to Avogadro's number. Now we've already talked about this, so I feel like we're past this part. We don't need to come back to this number right here. Okay, here's a couple different versions of the ideal gas formula. They are now pointing out that we can write this in terms of PV equals nRT, or we can write it in terms of big N, the number of molecules, times Boltzmann's constant. Now we had mentioned Boltzmann's constant before, 1.38, 10 to the minus 23rd, and Boltzmann's constant is big R divided by Avogadro's number. So that's how those numbers are related to each other. All right, here's a hydrogen atom mass. What is the mass of a hydrogen atom? That's one example. And then a second example, how many molecules are there in a liter of air? So those are two examples, and here we go. I think they're both looked at on this page. Here is an example, 1714. Here is example 1715. And we can take a look in the first one. What we're doing is asking what's the mass of a hydrogen atom, and the molar mass for hydrogen. And again, hydrogen is one of those isotopes where like 99.99% of hydrogen is just the simplest isotope. So the molar mass is a good representation of what the mass is for that particular isotope. And so it turns out that if we take that molar mass and then divide it through by Avogadro's number, it says that an atom of hydrogen is at 1.67 for 10 to the minus 24 grams. And if we put that into standard units, which would be kilograms, it comes in at 10 to the minus 27. Now the numbers of molecules, that's one example here. So just finding out what's the mass of one atom. This is a completely different question, so let's just be clear about that. This is saying how many molecules are there in 1 liter of air. So a breath that you take in. Now when you breathe in, I guess if you're breathing shallowly, maybe a liter is accurate. Your lungs actually will hold 4 or 5 liters. But this is just 1 liter that we're looking at. And here, again, we're using this formula using Boltzmann's constant and the number of molecules. And carrying out that calculation gave me 2.51 10 to the 22 molecules. Now again, it doesn't matter if this is nitrogen or oxygen or argon or water. That's how many molecules there would be in a liter of some sort of gas. The only thing we had to decide on here, I guess, was 1 atmosphere pressure, 1 liter, and then a temperature of 20 Celsius. So again, I'm using that 20 Celsius more frequently than 0 Celsius. All right, so here is a summary of what we've been looking at in Chapter 17. So all matter is made of atoms. Atomic and molecular masses are measured in atomic mass units. Temperature is a measure. Okay, I have issues with this. I still have issues with this. Saying that temperature is a measure of how hot or cold. It's a measure of how much, on average, kinetic energy the molecules have. Temperature scale, Celsius, Fahrenheit, and Kelvin. And then we move on to thermal expansion. We can approximate expansion using a linear formula. And then we move on to ideal gas properties here. So here are the properties of the ideal gas. It looks like we have a few more minutes here. So I'm actually going to step back to this example. I said that I had not read this carefully, and so I have to go back and redo this calculation. But let's do this instead. Let's see where I went astray. And what the problem told me was this. It told me that the temperature of the air in the tire is 10 Celsius, and then we drive for a while, and due to contact with the roadway, we end up at 40 Celsius. So the gas molecules are at a higher temperature. Now, a couple things we can point out here. First of all, if I go from 10 to 40 Celsius, how much of an increase is that in the kinetic energy of the molecules. And Celsius scales are not authentic. They're false scales because they don't tell us how much energy directly. So someone looking at this just new to the Celsius scale might think, oh, at 40 Celsius, we'll have 4 times the energy. Well, that's completely wrong. Celsius is very misleading. In order to compare energies, we need to use kelvins. So the first thing I want to point out here is the 40 and 10 conceptually are not giving us an idea of how much faster the molecules are moving or how much more kinetic energy they have. The other item, and this is the one I missed, is that it said that the pressure inside is 200 kilopascals, but it didn't say that was absolute. It said it was gauge pressure. Now, you guys know from chapter 11, I want to say, back in Physics 4a, looking at fluids, what we learned was that gauge pressure is not the same thing as absolute pressure. If my bicycle tire goes flat, what's the pressure inside? Well, if my tire goes flat, there's 1 atmosphere inside and 1 atmosphere outside. When I put my gauge on my bicycle tire, it doesn't read 1 atmosphere, it says 0. So gauges are telling us the difference between pressure inside and outside. So if I've got a gauge pressure of 200 kilopascals, what's the pressure inside? And the pressure is actually 1 atmosphere higher. And so what's going to happen here is the gauge pressure is 200. The absolute pressure needs to be 300. And so that's what I missed when I was writing this problem up. I apologize. I quickly read the problem and just thought that was the pressure and did not make an adjustment. So let's see what my calculations look like and see what I need to go back and correct. All right, here's my tire pressure problem before we start driving and then after we start driving. So before we start driving, I wrote the pressure down as 300 kilopascals. It's not right. I've got to add 1 more atmosphere onto that. This needs to get corrected so that it's 300 kilopascals. So, or 301, something like that. Now the pressure after is what we're trying to solve. Now the temperature that we start at was 10 Celsius. That's got to get converted into kelvins. And so I did get that, 283 kelvins, and then it's going to go up to 40 Celsius, that's 313 kelvins. Now once I make the switch from Celsius into kelvins, now I can look at those temperatures. Those temperatures now in kelvins are going to reliably give me an idea of how much the energy of the molecules went up. Again, Celsius is kind of a, it's not an authentic scale, but kelvins is. So we can see that going from 10 to 40 Celsius, it doesn't double the amount of energy, it less than doubles. What we want to think in terms of is the ratio, which farther down in the problem, I actually have it down farther in the problem, so let me jump ahead. This ratio of temperatures in kelvins says that the absolute temperature went up by about 10%. So when I start at 10 Celsius and go to 40, that's not like 4 times as much energy. The energy of those molecules only went up about 10%. Okay, so that's why we have to work in terms of absolute temperature scales in order to say something meaningful about how much energy there is, kinetic energy, in the gas molecules. So that's the point I want to drive home here. Now, the other assumptions that we're making here are, when I closed off, my tire doesn't leak. I guess that's the easiest way to say this. The tire is not leaking, and that means that N1 is going to be the same as N2. So if I go back and take a look at this ratio of the ideal gas law, the N's match, Now I can even do a little better than that, because the assumption we're going to make here is that the volume of the tire didn't change either. Now that's not quite true. The volume of the tire can definitely change. In fact, you know, when you're pumping up a tire, it goes from a little bit flattened to bulging a little bit. So we know that the volume actually goes up a little bit. And this is one of those tricky things in these kind of homework problems is, you know, sometimes the ratios are exactly 1. You know, the number of molecules didn't change. But other times we're making approximations. So the approximation we're making here is that the tire's volume really didn't change by much. Okay, I'm not sure with a tire. I guess I should look up some specifications and find out how much would volumes change. Anyway, since they gave us no information about the volume of the tires, we're going to go ahead and assume that the volumes didn't change either. So what that does with our ratio approach is that the volumes also cancel out. So the number of moles canceled out, the volumes canceled out, and what I'm left with is P1 over T1 equals P2 over T2, and I can write that down here. Now I left the V1 over V2 here, but we're saying that now is just going to go to 1. So that goes away. And then I wrote the ratio of temperatures. So if the number of molecules and the volumes are not changing, any changes in pressure are going to be related to how much the temperature went up. And that has to be a ratio of absolute temperatures. That ratio was 1.106, you know, a little better than 10, you know, between 10 and 11%, that the temperature went up, which means that the kinetic energy of the molecules inside went up by 10 or 11%. And in terms of pressure increases, that took me from 200 to 221. Now I got to go back and get this corrected, or maybe I will, maybe I won't, actually. But the change that I would need to make is, since it was a gauge pressure that we started with, this is going to be something more like 300. Okay, and since this is going up by about 10%, this is going to be 330. You know, 331, 332. So we can actually kind of estimate that right now. We don't have to necessarily get out a calculator. We have a pretty good idea of what those final numbers are going to look like. I apologize for not getting the right pressure in, but maybe that was useful, right? To see how we made an error. I made an error the first time going through this problem, and now we can go back and see exactly what needs to get corrected. And we can even, the numbers are simple enough that without a calculator we can get a pretty good estimate of what those numbers are going to look like. So, I don't know, what do you think? Should I just leave it in the notes? I guess I can make a second example of this and show what the corrected version looks like. All right, any questions on anything we've talked about today? So, I'm going to be around during the class time. I'm going to be around for office hours. Catch me on Zoom. So there's the Conf for Zoom schedule that's set up. And so check those times, pretty much Monday, Wednesdays, Fridays, most of the day. Check in with whatever questions you've got. Let's make this work as effectively as we possibly can by doing that. All right, so have a good rest of the day. Hope to see you in office hours.